Hello and welcome to the lecture number 9 of Physics 401A. In the previous lecture, we showed how Noethers' theorem can be used to show the conservation of linear momentum and angular momentum as the consequence of the symmetry of Lagrangian under translation in space and rotation in space respectively. In this lecture, we will be discussing the symmetry transformation of Lagrangian under the translation in time. Okay, so for example, in the previous version of the Noethers theorem, we did not mention any variation in time, and we also said that any variation of q and q dot, they should be independent of time, right? Either like a virtual displacement type, or very trivially they could be just constant displacement, constant variation type. Okay, now here we will be a bit more general, and we will consider the variation of generalized coordinates and velocities through time. So if you remember that time is the only intrinsic independent variable in the whole formalism, okay, starting from the method of calculus of variation, if you remember, and then q and q dot, they are basically the functions of time, but they also appear explicitly in the expression of Lagrangian. That's why we say that the Lagrangian may depend directly or explicitly on time, but also Lagrangian depends on time implicitly through its dependence on q and q dot. Okay. Now, in this current context, we consider a variation by time just by a constant amount. That is only for the sake of simplicity. Okay. And then we also consider that the variations of q and q dot are only due to their time dependence. Okay. Now we assume that the Lagrangian here in this case is independent of time. That means, so the time coordinates are changed, but the time coordinates are varied. Okay, that's what I said here. But the Lagrangian is explicit. It has no explicit dependence on time. So even if the Lagrangian changes or varies, that will be through its intrinsic or implicit dependence on time through q and q dot. Okay, so we can simply say del L del T is equal to 0. Okay. Now, how to mathematize or quantify the transformation itself? So the transformation is like that. T will be mapped to T prime, where T prime will be equal to T plus epsilon, where epsilon is just a constant. Okay, and Q will be Q prime, where Q prime will be now Q of that translated time, right? So the only variation of Q will be due to that variation in time. So if this is true, then we can easily write by using the expansion of Taylor, or the series expansion of Taylor, and writing the terms up to the first order, because epsilon, again, we are considering continuous type of transformation. So we can define epsilon to be the generator of infinitesimal transformation of time translation. So that's why epsilon is also, it's a smallness parameter. So we can simply write the q prime as q at t plus dq dt times epsilon, and dq dt is nothing but q dot. Now how q dot will change? So q dot will go to q dot prime, where q dot prime is, similar, in the similar fashion, will be equal to q dot of t plus epsilon, and that will be the same thing, q dot at t plus ddt of q dot times epsilon, and ddt of q dot is q double dot. So as a whole, delta L will then be equal to, okay, del L del Qi times delta Qi summation over I, okay, plus summation over I del L del Qi dot times delta Qi dot, plus finally del L del T times delta T. Okay. So this is how I write a general variation in Lagrangian. Okay. When we are considering that all these quantities q dot and t all are varied, then the Lagrangian is varied in this form. Okay. Now our Lagrangian is has no explicit dependence on time, so del L del T term will be 0, so it only has two terms, this one and this one. Okay. Now this and delta Qi and delta Q, so delta signs are nothing but the difference between the old and the new values. So for example, delta T will be epsilon, delta Q will be q dot epsilon, and delta q dot will be q double dot epsilon. Okay. So now we are writing what, the expression of delta L will simply be summation over I del L del Qi epsilon Qi dot, replacing the value of delta Qi over here, and similarly for the other term summation over I del L del Qi dot. Now del Qi dot delta Qi dot will simply be replaced by epsilon Qi double dot. Okay. Now as we are doing this expansion with respect to the real trajectory of the evolution, okay, then we can say that at the best trajectory the Euler-Lagrange equation is always valid, and that's why we can write that del L del Qi is nothing but ddt of del L del Qi dot. So finally, for our case epsilon is constant, so epsilon basically just comes out of the summation in any case. Okay, so epsilon just comes out over here, out of the summation, and you can write this term as this term as ddt of del L del Qi dot, because of Euler-Lagrange equation, times Qi dot, plus the second term will be given, again epsilon can come out of the summation. Okay, so summation over I del L del Qi dot, and Qi double dot will simply be ddt of Qi dot. So as a whole we can write this total this total contribution as epsilon summation over I ddt of del L del Qi dot times Qi dot. Now what is del L del Qi dot? We know for the case of conservative force field with velocity independent potential, del L del Qi dot is nothing but the conjugate momentum corresponding to the coordinate Qi, okay, generalized coordinate Qi. So finally we can write the whole thing as ddt of epsilon summation over pi Qi dot. Okay. Now we all know that was just an arbitrary variation of Lagrangian variation or change, I should say, because variation has a specific meaning. Okay, it's an arbitrary change, infinitesimal change in delta L. Okay, in L. Now, in order that this arbitrary change delta L be a symmetry transformation of L, that's exactly our objective, is to find the symmetry transformation for L. We need that delta L should be equal to ddt of epsilon times a function f, where f is a function of q and t. right? Now, if you remember what this is, then delta L is simply this. Now, because del L del T term is 0, now if we note what dl dt looks like, how dl dt looks like, you will see there will be two terms. One will be summation over I del L del Qy dot times Qy dot dot, that means Qy double dot, plus summation over I del L del Qy dot. So basically, I mean, sorry for this confusion. This term, this, I mean, okay, so this is somehow independent of this. So you can just write, okay. So there are two terms. Okay, these terms are coming from the dependence of Lagrangian over on the generalized velocities. This comes from the dependence of Lagrangian on the generalized coordinates. Okay, then if we just multiply, so the constant smallness parameter epsilon, we can simply say d dt of epsilon times L is equal to epsilon times summation over del L del Qy dot Qy double dot plus epsilon summation over I del L del Qy dot. Okay, and what is this? If you simply see this expression is nothing but the expression over here. Just you have to consider epsilon to be constant, right? This one and this one. And what is this? This is delta L. Okay, so basically we can say that the delta L which we calculated above is d dt of a function epsilon L, right? So finally we can write d dt of epsilon L is equal to delta L, and which is also equal to d dt of epsilon times summation over I pi Qy dot. So d dt of epsilon summation over pi Qy dot minus L is equal to 0. So epsilon times summation over I pi Qy dot minus L is a constant. Given epsilon is constant, this summation over pi Qy dot minus L is a constant of motion. Okay, so here we can finally see, I mean finally can obtain a constant of motion, okay, as a consequence of the symmetry transformation of Lagrangian through translation, or rather infinitesimal translations in time. And that is the third important conservation law which we can see by using Noethers theorem. Okay, and of course this one is not in general energy. This one can be, I mean, assigned to the physical property of energy only under this condition, that for us the system should be conservative and it should have a potential which does not depend on generalized velocity. The kinetic energy should be a quadratic function of generalized velocities, and finally the Lagrangian should be independent of time. That was of course our one of the primary assumptions. Then only this term will be given, I mean will give the total energy of the system. Okay, now there are some questions to think deeply. The first question is, here I showed that the delta L is a function of, so d dt times epsilon L. Now L is a function of q dot and t in general. So here L doesn't have any explicit dependence on time, I agree, but L has a dependence on q and q dot. Okay, so my question is that in some previous lecture we even in the first, when I was talking about the first version or the first the first step of the Noethers theorem, which were neglecting basically the translations in time on the variations in time, we said that for a symmetry transformation in Lagrangian, delta L should be df dt, where f should be a function of q and t only. But here the Lagrangian is in general a function of q dot as well. So are we making some mistake, or we can reconcile the fact? Just think. Okay. Another question is, what happens if del L del T is not equal to 0? That means the L contains explicitly the time. Just have a try. It's a nice home task actually, and let me know. And finally, we have said that our epsilon is a constant. If let's say epsilon is also a function of time, so the question is, if delta L del L del T is not equal to 0, or if epsilon is a function of time, will the conservation be always preserved or not? Okay, so think about this. In the next part, we will discuss some other important properties of Lagrangian formulation. Okay, thank you very much.